Baik, ini sudah sampai sudah 4 menit dari jam 2. Kita mulai saja ya Bapak Ibu dan beserta hadirin semuanya. Assalamualaikum warahmatullahi wabarakatuh. Selamat siang, selamat sore semuanya. Semoga dalam keadaan sehat dan menjaga protokol kesehatan. Pada siang hari ini kita beruntung sekali ya dalam agenda program Invitasi Ilmuwan Diaspora yang disponsori oleh Direktorat Pendidikan Universitas Indonesia. Kali ini kita menghadirkan narasumber yakni Profesor Dr. Wibowo Hardjawana dari The University of Sydney, Australia. Beliau akan menyampaikan materi tentang introduksi atau tentang pengenalan 5G, kemudian pengenalan Artificial Intelligence pada aplikasi 4G. Ya, sebelum kita mulai, saya ingin mereminder Bapak Ibu semuanya untuk berkenan mengisi daftar absen yang saya tuliskan di chat box. Jadi mohon untuk mengisi daftar absen. Kemudian ketika nanti ada sesi foto bersama menggunakan background yang sudah saya kirim lewat chatbox juga. Ya, baik Bapak Ibu, tanpa mengurangi perpanjang lebar ya, biar diskusinya nanti bisa banyak. Dengan hormat saya persilahkan kepada Pak Profesor Wibowo, waktu dan tempat kami persilahkan selama 2 jam ke depan. Silakan.
Terima kasih Pak Najib atas kesempatan ini. Bisa lihat screen saya ya?
Sudah Pak.
Sudah ya, kelihatan ya screen saya ya? Oke.
Ya, sudah.
Bentar ya. Ini caranya gimana ya? Slideshow. Oh, oke. Ya benar ya, slideshow jadi begini. Oke, ya. Oke, terima kasih saya sudah diundang untuk program diaspora ini. Presentasi saya hari ini bakal mengcover 5G dan aplikasi machine learning di area 5G. Saya bakal saya presentasinya bahasa Inggris saja, tapi nanti diskusinya kita bahasa Indonesia ya. Soalnya ada beberapa term yang saya nggak familiar untuk Indonesia dengan bahasa Indonesianya. Jadi saya bakal presentasi dalam bahasa Inggris, tapi nanti kalau bisa diskusi kita bisa diskusi dalam bahasa Indonesia. Oke. Kalau ada if any questions, please let me know. So the materials today actually is we have a lot of contributors actually for these materials. I mean we have Professor Fustik, and our postdoc Chang Yang and a bunch of my PhD students, basically. So you, Alpha, Vincent, and Sin. Some of them are Indonesian, as you can see from the names. Also, we have some contribution from other university, like National Taiwan University, another Indonesians, Victor Andrian, and also partly this work also is supported by Telstra, and we have that contribution there, and also partly is also supported by Most Micro. Telstra basically is, well, you all know, is telecom operators in Australia. Most Micro, on the other hand, maybe you guys not familiar. Most Micro basically is a system-on-chip company, SoC chips company. So they design chips especially for Wi-Fi. Wait, now I don't know why it's not working. Okay, so this is our center of IoT and telecommunication. So the director of the center is just a brief overview about our center. Well, you all know obviously about Sydney Uni, so I think it's maybe I don't really have to introduce Sydney Uni. Sydney Uni is the oldest university in Australia, and we have a center of IoT and telecommunication under the School of Electrical and Information Engineering. So our director is Professor Penka Fustik, and our deputy director is Professor Yong Hui Lee. Sorry. And we do quite a number of things like fundamental and applied research. And our teams actually consist like 9 academics, 7 postdoc, and greater than 40 postgraduate students. I think this picture is taken quite a while back, so it might change actually. We might go. Okay, so what we do in the center. So we do a lot of things, but mainly what we do actually we're doing on the wireless communications. Okay, so we provide innovative solutions, proof of concept, prototypings to industry in satellite, Wi-Fi, and cellular networks. So as you can see, we focus a lot on the wireless networks. From application side of things, we consider IoT, especially with application on power grid, industrial control, and as well like 5 or 6G. Okay, support fundings, well, we have, I think, excess of greater than 10 million in the past, and it coming from both Australian Research Council. I think, I'm not sure what's the equivalent in Indonesia, Australian Research Council, but it's like an Australian body for the research, and also industries. Okay, so an example in here, I think the one I'm going to give you, example in here for machine learning, I think that the work actually is, the support comes from purely from industry. So that actually is a very, very practical work that come from solving the problem that's faced by Tesla. Okay. So a bit about myself. I think maybe it's good to introduce myself because I think maybe maybe not many people, none of you guys maybe knows about me except Pak Ajib and maybe Pak Gunawan and some others academic in the UI that I met before. Maybe most of you are not familiar with me. I got my PhD in 2009 in Sydney Uni. My PhD supervisor, well, Professor Pankafusrik, basically. This is my PhD supervisor. She was my PhD supervisor. Then after that, I work as a research fellow. Then after that, I get DECA fellow. Basically, that's like an Australian government fellowship in which actually is you get academic positions, but you can just do research. So the focus on my research basically is on cloud massive MIMO. So after that, then I become, sorry, this typo. So I become a senior lecturer in 2019. So I just continue on my academic position. So I convert my academic position, become a teaching and research now. So when I teach several subjects, and the subject that I continuously teach year in, year out is basically wireless engineering. Okay, so my research grant basically, I think I obtained, I think is more than Australian dollar 1 million basically from the past, including my DECA fellow. I have like 2 patents. I think I publish mainly on IEEE journals. Yeah, because I think that's our requirement. So yeah, that's IEEE journals. So it come from like magazine, JSAC, GSDSP, and transactions, and one of it maybe is access. So yeah, so it's IEEE. So we are in our research in our group, basically we are IEEE oriented. So we don't really publish in any other venue other than IEEE for journal. Oh, okay, sorry. I thought it's chat is for me. So industry collaboration, we have a few industry collaborations. I work with Telstra. I also work with Huawei in the past. I also work with Moss Micro. So we deal in the different area basically. Academic collaborations, I think I just list a few here. We have worked with Chinese Academy of Science, National Social Science University, and I don't know, hopefully maybe one day, hopefully University of Asia. There is some directions towards that, but hopefully we can get it moving forward more and in more collaborations. Research students, I'm supervising PhD students, some PhD students, and also I'm also supervising like 2 accelerated coursework students. So typically in what they call in Australia, I mean like for those students that doing coursework like S1 or like S2, the thesis component is coursework. So I have a lot of them, but I have 2 that I accelerate. So when I accelerate means actually I choose the topics for them such that actually their topics actually closely related to our research, with the hope that we try to what they call in the future, they prepare them basically to do a PhD, be it hopefully of course it's in the uni, but if not then in other area, in other uni. Okay, so now let's go down to the business. So I think the topic is about for 5G, but I think it's a bit difficult if we start from 5G because we really need to understand what has been done so far, basically. Yeah, and before that, I think yeah. So we need to know what has been done. So I didn't talk about 3G here, but I will talk about 4G. So 4G basically started in 2008. So there is a bunch of release. Basically, you can see if you look at 3G, what they call? If you look at okay, if you look at what they call, if you look at the 3G PP, basically, you can see that actually there's a bunch of release 10, 11, 12, 11, 13, 14, and whatsoever. Okay, so that's what's 4G. Now, what scenario it support when you talk about 4G? All these things: device-to-device communication, machine-type communication, vehicle-to-vehicles. Okay. Now, the issues with that is that the support is very limited. Why? Because of the network design, not able to satisfy a high reliability and low latency requirement, as well as a massive number of devices. So it's not the technology. So basically, it's the design. There's a design issues in what they call in LTE that prevent LTE basically to be used, for example, for say low latency URLC requirement. So what's the goal of 5G? The goal of 5G basically aim to resolve some of this issue by trying to redesign the network from the basic. I'm not saying it's not compatible, but you try to redesign the networks. Now, wait, what is this? Okay, yep. So when you look at that, right? Now, when you talk about 5G now, when we talk about 5G, right? 5G basically, you can see how they define 5G. And the 5G basically is defined into three types of traffic. One is EMBB, another one is MMTC, the last one is actually URLC. So what's the difference between it? EMBB is like what you have now, right? It's internet. So then the goal is very simple. How can we boost the internet speed more? MMTC basically is massive number of devices, so like sensors, actuators, trackers, for example. Let's say you put in the car and you want to track the car because, for example, now let's say you have a fleet of trucks and you want to make sure that the driver doesn't go somewhere, for example, outside the route that he's supposed to go, right? So that's machine type communication, and typically in that kind of communications, the service basically is low rate data, low data rates. Yeah. The last one is URLC, ultra reliable low latency communications. So in this particular case, you have traffic with a specific characteristic with a low latency and extremely high reliability, meaning that actually you need to send this traffic with a low latency, and you got to make sure you receive that traffic. For example, robotic application, okay, or maybe traffic safety. So those kind of information, right, need to arrive within a specific period. Now, this the last one, he actually evolved further, because what happened is that when we do our research later on, as you can see, what we consider not just the low latency, we consider basically deterministic latency, meaning that we need to have a traffic that arrives within a certain latency range. It cannot be more than that, it cannot be less than that. So it needs to arrive within that particular latency range. That feature is called timeliness in what they call in 3GPP. That's a new features that's what we do in our research. You can see it later on, how can we design that by using AI. So this is actually highlighting the relationship between industrial body, like say 3GPP, and also IMT. IMT basically is ITU. Okay, so you can see how these players, including the companies, play about. So this thing established this figure actually showing you how they connected with, or they connected with each other. For example, 3GPP is actually developing the standard, IMT basically defining the use case and also the spectrums, and the companies basically is below here, product developments, and operators basically is network operation. Okay, so this is the key performance index of 5G. Well, I mean, you see this you see these things everywhere effectively. Okay, so it's defined by 5 things: big data, experience, data rates, spectrum efficiency, mobility. Also, not 5, more than that. Yes, so it's defined by all these, what do you call all these KPI. So this is the KPI of what you call of 5G. Sorry, I don't know what happened. So this is basically explaining on these on this KPI network, for example, peak data rates, user experience data rates, spectrum efficiency, area traffic capacity, network energy efficiency, latency, connection density. Now, one thing in here actually is the important here is that this KPI, right? If it's in a fixed wireless, if it's for example is a non-wireless network, right? This KPI maybe can be achieved easier. But in wireless, what the issues actually is that you sharing the spectrum and you sharing the medium. This is why achieving this KPI is difficult, because when you start to share something, right, you're going to have either interference or you're blocking somebody else. Okay, so this is the main problems in the wireless communication, and why the problem becomes challenging is because when you're talking about interference, right, they are interrelated with each other. So that means actually what one user do is going to affect the other user, because they are sharing they are sharing resources in this case. And that's what make wireless actually is quite interesting, because those relationship or those complex relationship, right, will allow you basically to exploit a lot of advanced tools that exist in the literature, because those tools actually designed to exploit those things basically. And this correlation, because there's a lot of research challenge basically in it, because you might think, okay, if I want to, how can I decouple interference, for example? So those things. Now, this is basically is the design principle, basically for the wireless communication. Sorry, yep. So basically is you have a wideband spectrum operations, and you also have the spectrum flexibility. So you need to think about it when you design about 5G networks. You have a wideband spectrum operations, and you have also spectrum flexibility. And you can see basically it's not just less than 6 gigahertz band. Now you're talking about 20 gigahertz spectrum band, right? So that means actually you're going to go up, and up, basically. So then there will be a spectrum flexibility here in 5G. So the next one is different, is that actually is that always on. So in 4G, typically your signal, right, is always on. In 5G, right, you try to figure out a way such that actually it's not always on, because always on is not so good, because one, overhead, the second actually interference. So then in 5G, actually there's a quest for redesign the systems. The next one is a forward compatibility. Obviously in here, actually, you need to have a forward compatibility so that you can allow support of 4G. So in fact, actually, for example, in here, the current 5G NR release 15, which is now is deployed, is not independent 5G. So it's called 5G NR non-standalone, meaning that actually, right, when you run it, you have a 4G as an anchor. So basically, you run together 4G and the 5G. So that's why it's called non-standalone. I think from next year onward, maybe people start to consider standalone. So the design principle here actually is that for 3GPP approach is to maximize the amount of times and resources that can flexibly utilize, that can be left blank without causing backwards, minimizing transmission of always on signal, confining signal channel for physical layer flexibility within configurable or allocable time frequency resources. So this is basically is just explaining to you what is the frequency range of the 5G. Yeah, because I think it's really important here, especially when we do research. What happened is that this frequency actually is give you a different environment. So for example, in here, designing a system for say millimeter wave, let's say 60 gigahertz, right? It's not the same with designing a what they call designing a system, for example, for the 6 gigahertz, because obviously in here for millimeter wave, you will not have as much as scattering effect compared to the compared to the 6 gigahertz. So obviously, if you want to design a system and you want to optimize it, typically what you want to do, you want to exploit some of the features, channel features, right? So the way you extract the gain is different. So now 4G use 15 kilohertz. I think we all know about this. It's using OFDM and it's also using 15 kilohertz. Now in 5G, you're using 15 kilohertz plus additional sub-carrier spacing, 30. You have it? Yep. 15 kilohertz, 30 kilohertz, 60 kilohertz, 120 and 240 kilohertz. So what's the benefit of doing this? Well, as you can know, right, that sub-carrier spacing determines the length of OFDM symbol. So if you have a sub-carrier frequency of 15 kilohertz for OFDM, your data transmission, right, your frame will be 1 on 15 milliseconds. Right? Now that will not be sufficient to satisfy URLC transmission. So because of that, right, you need to increase the sub-carrier spacing. Okay. So when you increase sub-carrier spacing, effectively what you're doing, you're reducing the time, the symbol time, the OFDM symbol time. So that means actually you're transmitting faster. So that's the whole idea of 5G and why people start to think about varying this thing. Now, when you vary this thing, right, another problem coming into picture, because what happened is then people start to we need to think, okay, if someone using 15 kilohertz, what happened if another person using a 30 kilohertz? And for example, if you do, for example, FFT on 15 kilohertz, then you combine it with a 30 kilohertz FFT, right? So what happened in here? Will you have an interference? So there's a new research problems coming into the picture when you have 5G. So this is the benefit for having a sub-carrier spacing, small and large, obvious. Small sub-carrier spacing had the benefit of providing providing a relatively long circuit prefix in absolute time at reasonable overhead. Higher sub-carrier spacing are needed to deal with increased phase noise and introduction of bandwidth and mini-slot transmission. So this is just the tech components. I just do this review so that it's easier for you guys to follow our research later on. So this is another components which actually you have the spectrum. So you get the FDD effectively and TDD, right? So again, when you're talking about massive MIMO, right, the design of these two are different because, for example, if you're talking about frequency division to let's say you want to implement massive MIMO on FDD, the research challenge or the research problem or the problem that you have will be different than TDD. For example, if you want to implement massive MIMO, for example, on FDD, your main problem actually is how can you recover the channel state information because you have a lot of antennas and those antennas is symmetric. On the other hand, if you're talking about TDD, right? Now your problem then, how can you calibrate the uplink so that actually you can trip that channel estimate uplink so that can be used for the downlink transmission. So there is different research problems. Same technology, massive MIMO or MIMO, but different problems depend on FDD or TDD. Okay, so this is basically another tech components at the physical layers for louder preference control signal first time domain resulting in lower decoding delay. So this is another key issues in 5G. 5G start to use a lot of better coder like polar codes. Yeah, polar code. That's right. I think polar codes start to come into picture in 5G because it can reduce the frame. And I'm not sure whether you guys cover in there, but basically, when when to achieve Shannon capacity, right? Your code need to be very, 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 very long. Okay. So now the issues actually in here, when your code is very, 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 very long, right? It results in long delay. So in the 5G, right? Now we got to figure out we have to shorten this code, but we still try to achieve close to Shannon capacity. Yeah. So that's the first item here. The second thing, at MAC and higher layers processing can be done without knowing the amount of data transmit critical for low latency, low rate uplink transmission in many IoT devices. So this is basically the tech components that we have in 5G. Okay, a bit more. So higher layer. So this is the one that I talked just now. You got is traffic quality, and plus one more thing. We need to think about the quality of service. Okay, now when you talk about quality of service, right? it can be because when you have a traffic web, you have a different quality of service, and therefore it is also depending on channel. It also depends on channel. So when you schedule resources, right, you need to take this into account. So in 5G, I think they provide these things in what they call in a better way. Yeah. So the second one is the use of LDPC and the polar codes. So no more turbo codes basically in 5G. Then the next one is preempted transmission. Basically, preempted means actually if a packet's coming in, then straight away you send that one. And also retransmission on the final granularity. So resources also can be scheduled in advance. This is actually related to this is an extension from the 4G, because in 4G basically we have this thing called semi-persistent scheduling. So in 5G basically is this function is extended. So that means actually in here, this is very important typically, for example, like low latency and deterministic traffic, because what happens is that you want to schedule the resources in advance so that actually you can achieve low latency, because we all know that if you have whenever you have a run request or access, that's equivalent to overhead. And we know that if you do wireless communications, right, that's equivalent to one loop round trip. Round trip is like round trip in 4G, for example, what can be, let's say, 7 or 8 milliseconds. So in some application like robotic, for example, they only have 1 millisecond. If you delay the what they call in some of the robotic application in which, for example, the robot actually doing maybe the application is for, like, for example, like a high-end manufacturing, right? That require, for example, 1 or 2 milliseconds. That robot will make a mistake already if you wait, or if you wait for the grant request. Of course, for example, if you use a robot, for example, like say an application in here, let's say for the supermarket in here, that's make no difference, right? Because 8 millisecond, 1 millisecond make no difference for application, for robot application for supermarket that pick up the correct items. Maybe it doesn't make much difference. But if you're talking about, for example, creating a circuit, digital circuits, or maybe like a high manufacturing, that can be a main issue. So the next one is another application here actually is the antennas. So you got a large number of antennas, right? In what they call in the 5G antenna that you can you can do beamform. Yeah. So at the higher frequency band is used to extending coverage, and at the lower band for interference avoided by spatial separations. And a new support for reference contrasting line channel state information feedback is required. So 5G basically increasing the MIMO capabilities further. And this is actually enable us to apply machine learning. Because what happened is that when you have these things, right, in 5G, right, things become much complicated. Larger number of antennas. And larger number of antennas, larger number of antennas, larger possible code book. And that's enable machine learning, right, to give us hopefully a better solution, because some of these problems basically is simply not solvable manually. Let's say, for example, you can't really say, okay, every time you go to manually adjust the beam, right? On another things to look at it, for example, sometimes when you wrote these mathematical problems, right, you end up with a very difficult problem. Let's say end up with a mixed integer programming problems, which is effectively not solvable in real time, right? So then machine learning basically come into picture to help solve these problems, maybe at the early stage, because sometimes actually when we do research, we found that machine learning is not stable sometimes, but machine learning can be used to facilitate these things, because machine learning is what machine learning is very good at. Machine learning is very good, especially if you do not have complete models and you do not have a closed form solution. Because machine learning actually is a kind of a model-free type of solver. Okay, so you given a certain models, but it doesn't know much about it, then the machine learn to solve that problems without you knowing what's happening inside, right? So typically that's the whole idea, effectively, for what they call for AI. So this tech component, basically those that 5G provide, actually gave you a lot of opportunity to create what they call to give you a lot of research problems in which you can use machine learning, which is previously is not possible. Previously doesn't make sense. Why it doesn't make sense? Because in the past, right, if the problem is simple, right, why do you bother using artificial intelligence? Nobody cares about artificial intelligence, because if you know the closed form solutions for it, there's no point for you to use that, because the classical techniques basically is more than enough to solve it, right? Only when you stuck with something, then yes, then machine learning come into picture. So that's basically the ideas why we start to do why we try to investigate and try to research on machine learning in wireless communications. So that's the motivation, actually, because when you look at the 5G system, right, even moving to 6G, they all become complex. Complexity is good for machine learning because machine learning, the assumption is that you don't really know the model. So that's why it's good. Yeah. So that's the whole idea. And this picture actually is just showing you basically is what exactly what the definition of channel in 5G. I put it here because when we do our research, right, we specifically focus in one of our research, we specifically focus on controlling one of them. So for example, in one of our research that's recently published, right, we focus specifically on downlink transmission, which is in this case, we specifically focus on controlling PDSCH, because we create a test bed, and then after that we prove concept basically that that techniques works and can communicate with the commercial mobile phones. So now, okay, almost finished. So now basically 5G NR, right? So that's basically the motivations. Now when you look at into details, right, the 5G NR can be divided into two. One is RAN, another one is core. So yeah, basically it's simple. Basically straightforward. RAN, radio access networks, responsible for all radio-related function, and core related to function that not in radio access, but needed to interface with the outside world. Okay, so that's the what they call. So that's the definition. Now, core network actually controlling RAN in some way. Of course, RAN is quite autonomous by itself, but core network in some way controlling RAN. Later on, you will see why I say that. Now, 5G can deploy, as I mentioned before, standalone and non-standalone. So this is a typical what they call typical connection between the 5G networks. Yeah. So the top part there, actually, you can see that's a control plane. So that's how you can control the 5G networks, the core networks. Now, there's a lot of function there, like PCF is policy control function, and I forgot what's the name of the rest. But one thing important here actually is the tool that connecting what they call connecting it to RAN and UPF. That means that's actually the access mobility functions, and the other one is session management function. Mobility function deal with the handover between base stations, and the session management functions handle the handle the IP allocation and the rest, because that session management function will be used to control the data traffic coming in from the internet into your radio access networks. So this is the connection between the core and the radio access networks. Yeah, so I think this is the basic overview. So I don't really go into details in this talk. I mean, this topic actually is covered in my unit in wireless engineering. So I took the overall description and explained it within 2 hours. So this is basically explaining what is the 5G core networks just now. What I explained just now. Yeah. Now, what is RAN? RAN is radio access networks. Now, RAN and core work together. Now, you can see in here, this actually is 5G, so therefore it's not E node B, but it's called G node B. Yeah. So you can see that the core network is connected to the G node B by using AMF and UPF as access, access and mobility management and user plane function. It talks to the G node B by using interface. Okay. Now, then this G node B then talk to the user. So this is the connection between the between the core network and the radio access network. And as you can see from here, right, actually core network in some sense driving radio access network. or driving base station. So this is the explanation of what they call orbit. Okay, so G node B manages the radio functions, and G node B is connected via interface. I think that's what the interface is called NG user and NG control. And XN interface connect G node Bs basically for what they call for active mode mobility, dual connectivity, as well as radio resource management function. Now, one thing new actually in here is that this G node B separation. When you look at G node B CU, right? Now they have separate. You can separate the function of G node B into what they call into a two unit basically. So I think that's quite new, because what happened is that it's as if actually you are separating physical and MAC layer in the different computers. Yeah, so I think that's the new thing about 5G. So this is the quality of service. How can the packets go from one side to another side? So you can see in here the packet, the user packet, functions, user plane function basically have the API packets. So you have the QoS flow there, then this QoS flow is mapped by G node B into radio bearer quality of service, then basically sent to IP packets. Why we do this? Because what happened is that in here, when we define quality of service, right? In contrast to what people are saying, basically, actually quality of service doesn't come from the RAN; it's come from the core, actually. So the core actually defines the quality of service. And once you go to the RAN, there is a certain mapping that you can do. So this is basically explaining what quality of service does. I think it's coming to the end here. So this is basically explaining how the RAN, what they call the RAN protocols works. Okay, so there is a control plane, there is a user plane. So in the sense, here basically is that user plane responsible for the data, control plane responsible for the control signaling. So this is the radio link control. Okay, so it's basically same thing. It's basically reside on that. So I just put it here for completion purpose. Oh, it's 5:45 already. So this is the media access control. I try to speed up so that actually we have time for discussion. So this is the media access control, which is below radio link control. So the goal for media access control basically is to handle resources, okay, to deal with resource scheduling and also hybrid ARQ transmission. Now, the brain of the 5G NR actually is a scheduler, okay? Because why I say scheduler? Because scheduler, I think, actually decided the type of the resources and the type of modulation coding you're going to use based on the channel quality, or what we call in 5G NR. And this is actually one of the research that we are doing. Actually, we do a lot of research in this area, and we investigate a way basically to deal with this scheduler to design a scheduler by using an AI. Okay, so I think this is the structure of it. So when we implement our research, right, actually we also follow this structure. Okay, we follow the structure. So we don't just, for example, build a model basically, but we follow the structure as well when we implement in our research. So that's why that's why I thought that actually initially when I thought that if I just present machine learning, right, for you guys, I thought that maybe it's difficult, maybe it's not complete, because I think it's the way I designed, the way we do the research basically. Let's say for example, if we design research on the scheduler, we do research scheduler, we develop AI for scheduler. The scheduler works exactly like that. So basically, then it's not complete. Now, 5G NR scheduler. So typically, what happens is that the scheduler is integrated in the MAC layer. Now, this is actually what everybody is doing now. Ericsson, Nokia, at the moment, everybody doing it. Ericsson, Nokia, Huawei, everybody do that. Okay. So now, scheduler control everything, effectively close to everything, resource allocations, transport format selections, and all the things. Okay. Now the issues in here is that when the scheduler integrated in the MAC scheduler, and you have a Huawei product, or you have Nokia product, or you have Ericsson products, right? the telecom operator, see, let's say Telkomsel, right, cannot change the schedule according to what they want. So this is the main things that also later on lead into our research. So this is the 5G NR scheduler. I think this is just a bit more explanation of the information that 5G NR scheduler take, basically. There's more information than this, but I think I just highlight the important one. Now, the last one is the physical layers, okay? So what physical layer does? Physical layer is responsible for coding, hybrid ARQ, modulation, and etc. Yeah. So I think this is what physical layer, it lies under the Mac. So physical layers take the instruction from the Mac. So it do whatever the Mac tell you. So this is basically explanation of all the channels in the physical, or they call in the physical layers. And yep, and this is, I think, is also the explanation of the channels. Previous one is a downlink, and this is actually the uplink channel. Okay. Okay, so this is the reference basically. Yeah, this is the reference that I use basically to talk about this. Okay, now, Pak Ajib, do you want to leave the discussion later on? Yeah, so I can finish all, then they can ask. Yeah, is that okay?
Yeah, it's okay. Please finish.
Yeah. Okay. Yeah. So now, based on that, right? Based on that, then we come to the second topic. Now, the issues in here actually, when we're talking about machine learning, we want to implement machine learning, right? In the 5G, 4G, or whatever wireless network. Now, the question in here actually is, it needs an input, and it also needs an output. So, what kind of interface that we need to develop for it? Because we need to effectively in here, what happened is that we need to open up the radio access networks, right? So this is the second topic. I mean, this is the one I'm going to talk about now. This is one of this work actually is supported by Telstra. So I just want to acknowledge Telstra here because they are very generous in supporting our work in this area. Now, what's the ideas of this? Why we want to do this? So the ideas in here actually come from the recent initiative by ORAN Alliance. Okay, so ORAN Alliance stands for Open Radio Access Network Alliance. So effectively in here, what happened is that in contrast to the traditional radio access networks, right? Each block in radio access networks now can come from a different vendors with a defined interface. Okay, so the idea in here is to open up radio access networks. Why we want to do it? There's a lot of motivation. For example, operators, for example, in here, well, you define the traffic already, EMBB, MTC, whatever it is, URLC, right? But it might be that operators have some customer that is more important than others. For example, maybe some customer pay double, although they're URLC customer, but they pay double more than the other one. So then these operators, right? He might think, oh, okay, whenever I see this traffic from this company, right? This customer, right? I better prioritize him over the other one because he pay more than the other company. Now, in the traditional RAN, you stop because what happened is that you cannot change anything. You got to go back to Nokia, Ericsson, Huawei, and tell, look, excuse me, I need to change this. Can you change it for me? Then what happened is, okay, extra cost. So ORAN try to prevent that. You try to open it up. That's why this area, this direction actually is driven a lot by operators like China Mobile, Telstra. I believe Telkomsel maybe it's inside. I believe, if I'm not wrong, I think Telkomsel is also inside, could be, I'm not sure. But I know it's driven a lot by China Mobile and Telstra. So this is the whole idea of ORAN Alliance, okay? So this is basically the architecture of it. So when you look at it, right, basically they try to, modularize all functions, multiple functions in multiple functions in the radio access networks. Okay, and also I think in here, when they modularize, right, they create a block like intelligent controller, near real-time intelligent controller, real times, etc. So that's what they do. I think they try to modularize the the function. So that's one. Then the second thing is that when they modularize the function, right, ORAN also actually what do you call it? Oren also actually is understand that coming to the future, right? You're going to have a lot of AI coming into the system. So they also try to standardize the implementation of AI. Okay, so that's the whole idea for this Oren Alliance. It's just come out, I think, recently. This standard. Now, when we work with Telstra, right? The problems that we are facing, I mean, the one that we do it, I think we do it before this thing comes. Okay, before this Oren Alliance come into picture. In fact, actually, we do the Oren Alliance just come into picture 1 or 2 years. We do this work with Telstra 3 years ago, basically, because at that time, Oren basically is still small, and we work with Telstra to drive the directions of this Oren. How can we do it, basically? I mean, like what things we can contribute from academic perspective. So Telstra basically Telstra discussed with us on that problems. So when you're talking about Oren, what they want to open up the scheduler, because what happened is that they have a big issues because, well, they want to control they want to control the resources, for example, for different quality of service, but they cannot. That's one. Okay, so then that's related then basically with the Oren. Okay, and in fact, actually, is what we do then actually is we show Oren actually our proposed interface. How can we open up the scheduler? So then that's what we do. So I think the one below here actually the reference implementation is actually our setup basically to create this to develop this interface. So you can see actually we're using software-defined radio with I think we're using SRS LTE 4G stack basically to replicate to develop the interface. So this is an example of interface that we develop. So effectively in here, what happened is that you writing a bunch of API, right, to extract those parameters. Okay, so you got a lot of parameters that we extract. For example, RTI, CQI, QCI, you can name it basically that list. Okay, we extract that information. When we extract the information, right, operators then with that can design whatever they want basically. How many resources you want to allocate to this guy? How do you want to prioritize, for example, for this guy? You can do that from the operator perspective. Okay, so that's the reason why we want to build this. Now the problem in here is that when we do that, right, then we stuck again because what happened? Oh, look, so there's so many parameters here. Now we can't just for every single customer or for every single changes, right? We manually we manually change the logic basically the logic for scheduler. It doesn't work like that because it's going to be very expensive. Okay, so then we think, how can we use the machine instead to generate the logic? So this is what we consider. This is, I think, is the application for it. So for example, in here you can see the open programmable scheduler basically providing the interface. Then after that we have an AI here that can be used then to serve time-sensitive networking. Why we call it time-sensitive networking? Because we specifically look for a traffic that require timeliness, meaning that actually that particular packet needs to arrive within a specific time. So for example, in here, we have a packet that needs to arrive within 2 milliseconds and 3 milliseconds. Cannot be more, cannot be less. So then we need to we need to figure out a way actually how can we generate the logic to do this, because that's the whole idea, right? When you use AI, you don't want to know how to you outsource your logic generations to a machine, right? You effectively you outsource to the machine and you ask the machine, please help me find this logic. Then after that I can use it, right? So you don't know how he generated. You do not know how he do the logic, or you do not know what's the mathematical function for that logic. But all you know is actually that you tell him, okay, can you tell me the logic? Then after they come back to you, okay, I give you this neural network. This is will generate the logic that you want. Okay, so that's the whole idea in here. Now, this is just explanation a bit about time-sensitive networking. So the important requirement here actually the timeliness. Why I mentioned this? Because this is where we're going to do our research basically. So timeliness, I think the one that we attack basically, because this is actually is very, very important for us at the time. And this is actually what the application case that we consider. So this is basically explaining why we want to do it, that we want to use the AI basically to design this logic. Now, when we design the AI, right, then we start need to think what kind of techniques we want to use: supervised, unsupervised, or reinforcement learning. So we decided at the time to do reinforcement learning in this particular case. Why? Because we want to adjust the long-term objective. Sorry, rephrase. We want to maximize the long-term objective by interacting with the environment. So how reinforcement learning works? In the simple nutshell, reinforcement learning works by an agent doing an action, test that action in such that actually it can get a feedback from the environment of the new states, and I mean get a reward, right? Get the reward from the environment. Then after that, also know what the current status, what the current state is. Okay, so effectively in here, what happened is that first agent look at the current state and make decision, determine an action. 2, quality of action is assessed at the current state are assessed. Then 3, rewards or penalty with respect to long-term objective are awarded for selected action. So that's the what they call that's the basic of reinforcement learning, right? Now there is 2 types of reinforcement learning, regardless what the variant is in the literature. One, neural network based, right? And the second one is table based. Table based is a standard Q learning base. So table based basically is like the top one. So you have a Q tables effectively in here. You have a current state, you have reward penalty, then you just come out an action. Okay. So you have you just look at the table. Now, one issue in here is that when you have a large table, right, then you have a problem in this, what they call in this case. The second one is neural network based. The logic learned based on multiple weight equations. This I give you, I think I draw here basically it's just a neural network with the 2 hidden layers. So current state, reward penalty coming in, then after that latent action. So in our research, we decided to do the later, the neural network based. So that's led into this research that we are working at, the knowledge assisted deep reinforcement learning in 5G scheduler design, from theoretical framework to implementation. This work has been machine learning. I think has been accepted in the JSEC special issue on machine learning for wireless networks. It's not machine learning, it's a special issue on machine learning for wireless networks in 2021. And the draft is also available in Arxiv. Okay. Now, we talked just now about the time-sensitive networking, right? So this is just the introduction, basically. Now, the wireless scheduler here is a multi-dimensional function. Take the input, right, which is just before we talk about it, CSI, and also the Q state information. What is Q state information? You will see it later. I just draw it. Then after that, it output the amount of resources at every transmission interval. Okay. So motivation. What's the model? So effectively in here, you can see that you want to design a wireless scheduler for time-sensitive traffic by using deep reinforcement learning. So with a timeliness requirement. So this is a time-sensitive traffic for different users coming to downlink scheduler and delivered to the user. Now you want to make sure the end-to-end delay, right, is between that dmin and dmax value, because it has a timeliness requirement. Okay, so that's the whole what they call that's whole ID. And a way to measure is actually also use the head of the line delay. That consider that how long you take when the packet actually is right at the beginning of the packet actually is at the head of the line. Why we use DDPG? I think DDPG stands for Deep Deterministic Policy Gradient Algorithm. Why we want to use that? To design a scheduler to provide what they call, first, DDPG is reinforcement learning. So we use, so we just what we discussed, we want to use reinforcement learning, right? So now we want to use actor critic DR algorithms because of the issues in the standard problems where you have class action and state spaces. So therefore we can use actor critics based on the neural networks. Yeah. So I think that's the whole idea. Now, one thing in here is that the problem here, we try to implement the standard actor critic DRL algorithms, which is the best one so far, I think, as far as I know, is DDPG, Deep Deterministic Policy Gradient Algorithm, invented by Google. No, I think maybe Google is the first one to bring up this one. However, that one, right, if you just plug that into the problem that we have, somehow it doesn't work. So you will see it later on, why is that the case. So before that, I think I just do an overview of the standard DDPG, Deep Deterministic, Deterministic Policy Gradient Algorithms. There is 4 components. 1, replay memory. What's the goal of replay memory? Replay memory, the goal is storing action and reward that resulting in transition from state T to state T plus 1. So it's like storing a memory in your, for your neural networks. Then the second one actually is the states. So when you define the states, right, you need to define the state of your system. So the state of the system, we define the state of the system, right, when we implement standard DDPG, is actually in terms of delay and SNR. Okay, so this capture actually the state, the delay state and the SNR states of the system. Now, action, in terms of action is the number of allocated resources for each user. Rewards actually is 1 only if a user K is successful in decoding packets and arrive with timeless requirement. Other than that, the cost is 0, right? Because you don't give any rewards, basically, in this case. So this is basically the standard DDPG. And if you want to implement standard DDPG in our works, this is how we model it. So how does exactly it works? So for specific states, right, this is the picture here. For specific states, actor, GNN, will generate an action. Then after you get an action from the environment, you obtain instant reward based on an action. Then you store the corresponding transition state, reward, and action in the replay memory. Then what you do then after that, you calculate the long-term rewards, which is a Q value, effectively, right, for actor by using a neural networks. So that's the first neural network because actor is a neural network. Deep neural networks. After that, right, you then select the history from the replay memory for the critic DNN to compute the Q value, because now you want to provide the critics on the quality of the choice by the actors. And next one, you need to compute the loss function for actor and critic. Then you update the NN based on 4, which is 4. So then that's actually where you update the weights for the actors, the DNN weights for actor and DNN weights for the critics. Okay. So that's where you do it. So this is what you do in the training mode. Obviously, in the validation mode, you design the actors, then you just throw in the states, then everything works in a similar way. So this papers, I think, is this slides actually is written partly by my students. So in the first contribution in the papers actually is you propose a theoretical DRL framework. So what happened is that we modify the way we do the what you call the modeling, right, to be simpler, to be precise. Actually, in here, what happened is that we don't just use the tools, machine learning from computer science. What we do in here actually, because in communication, we also have theoretical model. So what we do to reduce the complexity to be specific action space, states, and reliability, right? And evaluation reliability, what we do actually, we use theoretical model. So when we use theoretical model embedded inside, we're able to improve the training efficiency, because a lot of, when you look at the standard DDPG or standard deep reinforcement learning, right, in the what they call in the literature, typically most of them are submitted by computer science. They're good, they're excellent, but in our application in wireless communication, right, I think we can make it a bit better, because in communication, actually, we already have some theoretical model in which actually we can embed them together. We can make them work together so that actually it can complement and improve it. So I think that's the whole that's the whole idea in here. So in the our first contribution here, I think we are one of the first that consider embedding theoretical models into the things. For example, when we say theoretical models, we're talking about Polyansky equations, for example, that predict reliability and the decoding rates. Okay, so this established already a closed form solution that established connections between reliability, coding rate, and frame size, I think, for Poliansky. Then with that, we embed that inside, then we use this actually as a way to simplify the decision of the neural networks, which is actually interesting that we found actually improving the coding efficiency. We do not have theoretical proof, but intuitively, right? Because we reduce the action space and the states. As a result of that, right, it's a bit easier for you to find a better solution. So therefore, the training improved. So this is basically explaining what we do differently. So you can see in here what we do differently when we embed theoretical models into the what they call into the deep into our deep reinforcement learning framework. When we embed theoretical model inside deep reinforcement learning framework, right? What happened is that we have to change the action and we also have to change the reward as well. But when we change it, you can see that actually, for example, for the action, right, instead of number of resource blocks, because then, for example, in here, you have a lot of combinations. If the number of resource block is, for example, 25, right, and you have a use 20, what do you call? You have a user K, you're going to have a lot of combination there, basically. Now we change it, for example, in here into just a binary, basically, because we're using theoretical models to compute the resource blocks needed. So we try to simplify the what they call the framework, the DDPG framework in the literature, such that actually we can then use what they call so that actually we can make our life easier, so that actually we can find the better solution. So I think this is the whole idea of this this is the whole idea of this paper. So what happened in here? When you look at this example here, this result, right? When you look at the color there, 1 means actually is loss, 100% loss. 0 basically is less loss. So you can look at the result here, the original DDPG, right? And also the DDPG, but in our theoretical framework. So you can see actually there is a improvement here. You can see actually the packet loss ratio is going down, right? And why we have this? Well, one, basically, right? We use the theoretical, we use the theoretical models, basically, to simplify. That's one, so that we can find the solution easily. The second one actually is that we use the, we use the, we use the, we use the DPG, right? I mean, sorry, the first one actually, we use the solution can be easily found. Then the second one actually is that when you look at these figures, right, because the solution, how to say, yeah, I think it's maybe that's the only one. So the solutions, you can easily find the solutions in here. Oh, sorry, the second one actually is that because you embed constraint when you simplify, because you have that theoretical knowledge, theoretical model, right? When you have the theoretical models, right, what happened then basically, you will have the, you already embed some sort of like quality of service. If you do not have that, when you use the deep reinforcement learning, right, you got to ask the neural network to find or to satisfy that quality of service. And that's require neural network to be smarter, because neural network doesn't have that knowledge. So the lesson learned in here is that when you want to ask someone basically, or when you want to outsource your logic design to someone, you need to give that guy the best information possible so that he can design the best solution. So this is the whole idea here. So when I'm saying it, when I say give him the best possible information, I give him the best possible theoretical knowledge. So that's why there's a lot of improvement. So the second contribution here actually is that you embedding all this quality of service. Okay, so now I think there's a picture. Now this picture is important because when we do that, right, what happened is that we also change a lot, because what you can see is that in the standard neural network DDPG, right, for the one implemented with Google, for example, They only consider single critics. So we change it to become multi-head critics. That's one. The second thing in here is that you need to reward, you need to shape the rewards to do with timeliness. Okay, that one is actually engineering issues, engineering features, so that's no problem. But the last one here, right? This is actually, in fact, is a problem, which is maybe similar with other area. So what happened in here is that when you train your neural network, sometimes your neural network do not have enough sample for a specific scenario. So because of that, right, you have a big problem in approximation. So this is where we use a technical important sampling. So effectively in here, what we do actually is that we weight the sampling, or we select the sampling that is important to be what they call for the network to train. So it's not just we just anyhow randomly take the samples, but we select a specific sample, right? That we select a specific samples that you can that you can use that is important for the neural network. Because, for example, in here, right, not all the samples that you use are important for you. Yeah, because, for example, in here, maybe a good example is a share market. I think is in share market, for example, I think is Nassim Taleb, I think is talked about the black swan event. So basically in here, is given like say you have a lot of white swan, right? What is the probability of black swan suddenly appear out of nowhere? So this is a similar things, because what happened is that this black swan, right, this less sample event, right? You don't have that. So therefore now it's very important to choose the sample so that actually this sample can cover the whole case. So you need to think here actually which one is the important sample. So this is another thing that actually we embedded into the DDPG that is not done before. So this is the results when we do it. Now you can see when we do that, right? There's further there's an improvement as well. You can see the figure C compared with the original one. So you can see there's a significant improvement in here when we do that. So this is another result here during the for the user. So basically this is the origin. When you look at it, obviously we try to show our research is the best one, obviously. So you can see that the multi-head critics with the reward shaping basically, and also with the multi-head, right, is performed the best, right, in terms of rewards. So I think that's what we're trying to show. So comparably with other scheduler, you can see there's a 30 to 50% less packet loss with our techniques compared with like early deadline first. I'm not sure what maximum throughput and round robin. So this is the result that we have. Now, when we do when we do that, right, this is bring to our third contribution, because now what we talk about is theoretical machine learning. Right? We talk about theoretical machine learning, but now typically now we do not just want to have a theoretical. We want to test it. We want to prove a concept whether it works or not. We want to test it on the real system. Okay, because at the very least we have a test bed or we have a reference design or can see, oh, okay, there's a possibility that this can work in real world. Obviously, we cannot bring this to real world because we don't have the network, we're not an operators. But at the very least, we can test it in our lab by using a real protocol stack. So this is the setup that how we do it. Obviously, in here we use GPU. Okay, we have a server and we have a GPU running for the neural network, and then we also have a EPC, right? SRS Inode B and SRS EPC. Basically running on the computers as well. Then what we do actually, we measure end-to-end latency. This is actually 4G networks because we don't really have the 5G stack in our lab at the moment. At that time, at the moment, I think we don't have it still now. So that's why we use a 4G protocol stack. So then you can see in here actually is we have a bunch of software-defined radio kit from a national instrument. Okay, so one of them act as a RF for the base station, and the other two actually act as the RF for the user. And then the neural network, the DPG that we designed, is trained by using the GPU put in the edge server. Okay, so that's the whole setup here. How can we deploy this system? So when we look at that, right, we have this. This is the target latency bound. We target 9 to 11 millisecond. Again, this number actually we just plug it from the air, because obviously if you do 5G, you obviously will not put 9 to 11 millisecond. You put 1 to 3 millisecond, for example. But it will be the same algorithms that can be applied. Okay, we put 9 to 11 millisecond because effectively in LTE there is no way you can go beyond 4 milliseconds. Regardless how you design it, you will not go beyond that. So this result actually is the result of the latency and that run in the prototype. When we run that system, when you run this one in the lab, this is the figure. This is the result that we have. Okay, so my student actually have this video. I think you can have a look. This actually is a real It's a real experiments that we run in the lab. So you can have a look at this. Just give me a minute. Let me turn it on. Maybe. Oops, sorry.
Mungkin bisa diberikan link YouTube-nya, Pak?
Ya, bisa.
Iya, karena suaranya nggak muncul.
Oh, sorry. Oh, suaranya nggak muncul ya?
Iya, harus ada setting kecil sih di bagian speakernya.
Oh, harus ada setting kecil. Jadi aku ke YouTube dulu gitu ya?
Mungkin kasih link YouTube-nya aja biar everybody can see.
Oke, bentar ya.
Ya.
Bentar. Bentar. Tunggu. Aku keluar dulu bentar. Bentar ya. Aku kayaknya bisa run di ini deh. Kayaknya aku bisa run di. Kayaknya bisa run ini deh. Aku run pakai YouTube-ku aja deh di sini. Aku buka di YouTube-nya aku deh. Bentar ya. Library-ku. Bentar ya. Oke, bentar. Dengar suaranya tadi?
Belum.
Oh, bentar ya. Coba ini bisa nggak di sini? Kalau nggak bisa aku kasih.
Saat Pak Wibowo share screen, di situ ada di pojok kiri bawah ada share sound juga. Nah, itu diklik. Kalau diklik itu nanti suaranya bisa muncul.
Share apa?
Share screen. Di pojok kiri bawah itu ada share sound.
Pojok kiri bawah ada cell phone.
Share sound.
Oh, share computer sound. Oke. Share computer sound.
Ya, share sound. Ya.
Oke. Oke, bentar. Kalau gitu ke PowerPoint aja. Bentar ya.
Iya.
Oke. Mana PowerPoint? Oke.
Screen.
Oh, check. Oke. So bentar tadi.
Coba sekarang.
Hello everyone.
Okay.
This is Doyo. Today I will do a demonstration, and this is an industrial project in Lab. What we will show in this demonstration is the AI-based programmable scheduler in the 5G IoT test bed. Well, the server will automatically program a neural network as a scheduler that will be deployed in 5G base station. And we will use this scheduler to achieve deterministic UILC in the network, where the latency or the delay of the data packets that delivered to IoT devices will be stabilized at a specific value. The following is the web user interface of the 5G IoT testbed running in real time in our SDN lab. And we will try to deploy 3 different neural networks, and the real-time latency of the packets is measured here. Let's first try to deploy an untrained neural network with random neurons. As you can see, after we deploy such neural network, the latency of the packets start fluctuating. And let's try different neural networks. Here we deploy a trained neural network that targeting 10 millisecond latency. As you can see, after we deploy such neural network, the latency will be stabilized at our desired value 10 milliseconds. We can also try neural networks that targeting lower latency, for example, 6 milliseconds here. And after deploy such neural network, the latency will be stabilized at our desired value. So what could be the potential applications of this system? First, we can use it to support mission-critical IoT services, where data packets must be delivered at a specific time. For example, robotic control in manufacturing, car control in autonomous driving, inverter control in energy grid, and healthcare device controlling. Furthermore, since these services may have different requirements in terms of throughput, latency, and reliability, we might use AI to optimize the 5G IoT networks for each of these services and support these services simultaneously in one network. This will allow operators to share one infrastructure among multiple IoT services, which is referred to as network slicing. Thank you for watching. That's all for my today's demonstration.
Okay, so
hello.
Okay, so that's basically is the video that my student make on the to describe the project. So that one actually is because when we do the project with industry, I think the industry specifically asks us, okay, well, you do our research, you do the research, that's good, but you got to show it to us whether it really works or not in reality, because we don't want to just see those theoretical results, which that doesn't work in practice. So I think the industry, when we work with industry, I think they expect us basically to do that. So therefore, we spend a lot of time basically creating the setup, and I think this research actually, in fact, we found actually is quite well. It's hard and rewarding. It's rewarding, it's challenging, but it's also quite hard actually. So basically, this is the conclusions of this particular research that we have. So the conclusion here actually is few things. One actually is that we need the expert knowledge. That means actually theoretical model. So we need to if you have a theoretical model, right, and you know your theoretical model is accurate, you can use that to improve the neural networks. Okay. Now, this is what we found in the MAC layer, in the scheduler level. But when we do the physical layers, we have interestingly, we have a different results. Okay, we have different result in what they call in the physical physical layer. So it's quite interesting actually, in which that actually when you apply neural networks, right, in the different layers, somehow the insight actually is a bit different. Yeah, that's the what they call, that's the things. That's what we found in here. The second thing in here actually is we learn, like we learn, I mean, like in here is that when we have a system, right, we got to be able to demonstrate that system works, because I'm not sure in Indonesia, but in Australia, I think now that's the way it goes. Because whenever I work with industry, for example, even with Micro or with others, they always ask you basically, okay, how can you show us it works? Basically, I mean, like, at least we need to see some evidence it works before we want to collaborate further. So therefore, I think this is what we are doing, what we do there. Then finally, the third one actually is that there's a lot of good machine learning techniques in the literature, but I think sometimes actually those techniques actually is quite general. So therefore, if you have a specific, what do you call that, specific use case, right? It could be possible basically for you to modify that and to propose a certain framework around it, improving it basically. So it's not totally brand new techniques, right? If you look at it, basically, we don't say, well, we invent a new neural network techniques. We don't. But what we do actually, we use the existing techniques and we leverage and we improve it by embedding a theoretical models or by including important sampling, etc., to adjust according to our specific problems. Because some problem actually is quite specific. So I think that's the whole lesson here actually when we do this machine learning research for scheduler, for MAC layers basically. Now we now actually is also expanding in other areas. So this so now I think I'm trying to list out some of the topics that actually is ongoing in our research. Yeah. So we based on that result actually with my student Charles for the scheduler, we conclude that I think, oh, maybe machine learning is not a bad idea, because previously, to be honest, actually prior I'm engaging machine learning, I'm quite skeptical as well. I mean, our lab, in fact, Franka and me, basically, in fact, we're quite skeptical with machine learning because it's simply very difficult to see how it works, because there is no model whatsoever, but seems actually it can work. We do not know why still, but somehow actually it can work. Okay, so then it's quite interesting actually to explore this area. Of course, our classical area is still very good, but it's interesting to explore these topics basically in what they call in the research area that we are doing research basically. So this is the list of the other topics that actually we are also doing research. For example, in here we're considering a network slicing. We have this prototype as well. This is done by our master students. So basically, I think it's those students like they're doing a master by coursework, and their thesis basically is result in the papers, which is this network slicing. So one of them actually write a papers in PRMRC, basically. So I think submitted in PRMRC about network slicing, and the code is available in GitHub. In that one, you can just, if you can replicate the setup there, you have the equipment, you can just go to that you can just go to that GitHub basically, download it and run it basically in your lab. So what's the idea in here? The idea is actually very simple. How can you create multiple slices? That's all. That's what he did. So when you look at it, basically, effectively in here, each slice has its own scheduler and has its own resources. So basically, it tried to create an isolation, a network isolation, basically, between slices. And once you create the network isolation between slices, then this isolation configuration then is relayed back to the 3GPP or 4G protocol stack. We're using SRS-LP as well in this case. So I think so that's what this paper does. So this work actually is ongoing because I have also another master student, right, that now actually expanding, considering the uplink and also the carrier aggregations. Another example here, actually, this is that we also considering is a 6G waveform. In 6G, I mean, like OTFS, orthogonal time frequency space modulation that has been proposed as the as the 6G waveform. It's proposed, I think, 2 years ago by Coherent Technologies. Now I think they're considering it for the 6G. Why they consider for 6G? Because this waveform is very suitable for scenario in which you have a high Doppler spread. Okay, an example here, like the picture that I show you just on the text. You have a car, you are in a car, right? You're driving here, then in a highway, for example, when the base station transmits the signal to you, right? The base station basically just broadcasts, right? So you will receive signal from a different cars, okay? Reflection from a different car, reflectors. So these cars all maybe traveling with a different speed. So as a result of that, right, you're going to have a high Doppler spread. That means in here, your signal is seen as if actually is what they call it, is non-stationary. Now, what's the ID here or TFS? The TFS actually, as if actually is it make the signal as if seen at the receiver as stationary. How the OTFS does that? OTFS does that by spreading and multiplexing the symbol in daily Doppler domain across standard time and frequency OFDM transmission. So because of that, they've been seen as static for the long period, let's say 10 milliseconds, or I think even 100 milliseconds. So we're doing research in this area. So what we do actually, we try to figure out how can we use AI to develop a detectors. Because what happened is that when you do this, right, in this system, right, the matrix is large. When the matrix is large, right, signal processing becomes an issue, especially in detectors. So we try to figure out AI, for example, in here, how can we do that? Another topic actually is basically improving rate control, basically. So that's another topic that we consider. So we try to use AI basically to predict data rates, basically, effectively. We try to predict the modulus encoding scheme, what type of modulus encoding scheme that it should be used. This thing actually is, we apply this actually for Wi-Fi at the moment. So we consider this a scenario for Wi-Fi. So this is another topic. This is an example here. I think this is done by one of our coursework bachelor student, and he's very good. So that's why he come up with this. The next one actually is, we also, of course, because I come from physical layers, so I course one of my major topics, my major interest actually is MIMO, because my PhD thesis actually is on MIMO as well. So my interest is on MIMO. Now, when we do MIMO, we do a lot of research on MIMO. We consider like collocated MIMO and distributed MIMO, basically. So then again, what's the idea in here actually? We want to figure out a way, how can we reduce the signal processing complexity. So the idea is in here, we try to figure out how can we use AI, if it's executed across after train, right, can give a good performance with a low complexity. Okay, so we investigate multiple techniques like GNN, DNN, and all types of what they call all types of techniques. So this is another area that we consider. So okay, so I think now this. So I believe actually now it's 6:32. So I leave more than half an hour, I guess, actually for questions. So that's conclude my presentation. So if you have any questions, feel free to ask me. If you don't have any question now, you can email me. Then I will answer the questions. So I think I'm open. I think I can open for discussion, Rajib, I guess.
Okay. Thank you very much for very interesting presentation, Prof. Wibowo. Actually, I think the most interesting part, according to my opinion, is realizing the theoretical framework into the realistic implementation. I think I'm very much likes to the video that you already demonstrate to us. Yeah, I think everybody agree with me. And then times to questions right now. Ya, jadi mahasiswa S1, S2 silahkan bertanya. Ini mumpung ada narasumbernya yang sangat kompeten. Silahkan bertanya apapun lah ya, terkait dengan topik ataupun mungkin sedikit melenceng masih dalam bidang telekomunikasi atau studi, very much welcome lah ya. Oke, silahkan kalau ada pertanyaan. Mungkin dengan voice atau dengan menuliskan di chat box kalau malu-malu. Nanti saya bacakan. Ya, silakan. Mungkin dari siapa nih? Aduh. Mirza, mungkin Mirza ada pertanyaan, Mirza? Halo Mirza.
Ya Pak.
Ada pertanyaan nggak?
Untuk topiknya, maksudnya masih kagum gitu Pak. Itu untuk ditanyakannya terlalu apa ya, gimana ya? Mungkin harus lebih didiskusikan lagi terkait penerapan machine learning di teknologi 5G khususnya. Tapi saya juga ingin berdiskusi gitu Pak. Maksudnya untuk AI ini bisa diterapkan, maksudnya gini, 5G ini untuk AI ini untuk diterapkan ke teknologi 5G sudah terbukti dengan bisa ada penurunan paket loss yang tadi didemonstrasikan gitu. Tapi ada hal lain selain AI ini untuk menjadi concern ke depannya tidak? Khususnya tadi Bapak demonstrasikan bahwa ada sebuah algoritma yang bakal bisa, beberapa algoritma yang bisa diterapkan di teknologi 5G ini gitu-gitu Pak. Nah, kebetulan itu Pak satu, terus yang kedua saya juga kebetulan sedang meriset dengan Pak Ajib terkait di physical layer untuk bisa meningkatkan spectral efisiensi gitu Pak dari berbagai algoritma. Menggunakan beberapa algoritma yang menjadi ada paper acuan saya. Namun di sini masih lebih ke bagaimana penerapan AI ini di teknologi IoT juga gitu Pak. Seperti apa? Untuk mungkin ke depannya kalau bisa diterapkan itu seperti apa? Itu aja Pak. Terima kasih.
Just to answer. Sebenarnya AI itu gimana ngomongnya ya? AI itu sebenarnya masih, kalau menurut pandangan aku, sebenarnya masih lebih kayak unproven teknologi. Kenapa? Kita udah tunjukin di research kita itu visible, ada possibility bisa di-apply. Tapi masih banyak masalah yang belum jelas. Jadi misalkan contoh, kita kan apply AI, kan, kita udah training networknya, udah jalan. Nah, tapi terus pertanyaannya, ada 2 pertanyaan at least yang mesti dipertanyakan. 1, berapa cepat sebelum dia bisa convert ke solusi? Ya kan? Itu kan 1. Kecepatannya harus lebih cepat dibanding kecepatan perubahan di wireless network-nya sendiri, ya kan? Soalnya kalau kayak coherent bandwidth. Jadi kalau misalnya kamu AI-nya converge-nya lama, sistemnya udah berubah, nggak bisa jalan kan? Itu 1. Yang kedua, ada juga challenge misalkan, kalau kamu udah train network-nya, terus gimana caranya itu? Nanti kalau kan data itu kan datang terus. Itu bagaimana kita treatment-nya? Apa kita pakai transfer learning atau kita pakai apa? Itu masih belum jelas. Jadi ini sebenarnya kalau menurut aku sekarang ini kita baru mulai, kita baru investigate bahwa possible untuk implement AI segala begitu di Mac layer atau mungkin even di physical layer, itu possible gitu. Kita baru sampai level itu. Jadi aku rasa ke depan masih banyak possibility. Nah, sekarang challenge-nya kalau menurut aku itu. Jadi pas kita implement AI itu bagaimana implementnya? Apakah kita tinggal tancepin aja atau kita mesti rubah sesuai dengan keadaan dengan problem yang ada. Kalau kita cuma tancepin aja, wah bermasalah kan? Berarti nggak ada research-nya kan? Kita kan cuma tancepin, cuma aplikasi kan berarti kan? Tapi kalau misalkan bisa dirubah sesuai dengan kondisi problemnya ya, problem use case scenario problemnya gitu kan. Nah, itu lain gitu. Jadi kita bisa jadi research jadi tergantung bagaimana. Jadi key-nya aku rasa mesti identify problemnya. Jadi kayak contoh tadi yang aku taruh di situ, itu kan aku berusaha menunjukkan bahwa sebenarnya itu kita pakai teknik yang biasa, tapi masih ada kelemahannya gitu teknik ini. Makanya tuh kita bisa fokus sesuatu yang berubah. Jadi itu Itu kalau menurut aku, pandanganku begitu. Karena kita di engineering, jadi aku rasa kita nggak mungkin. Aku rasa kemungkinan besar aku nggak. Karena kita di engineering, jadi kita kemungkinan nggak invent new di DPG. Jadi kita lebih kayak modify di DPG bagaimana, atau customize neural network kayak bagaimana. Jadi pikiranku begitu. Ke depan masih banyak masalah, terutama physical layer. Physical layer karena physical layer itu lebih baru, dan physical layer itu punya stringent latency requirement. Jadi kalau misalnya kita di Mac layer, kita bisa cuman latency requirement kita misalkan mungkin cuman I don't know 5 millisecond, 4 millisecond, atau minimum misalkan 2 millisecond, ya kan? Nah, atau 1 millisecond, kita masih bisa jalan. Tapi AI-nya bisa jalan. AI-nya masih nggak begitu masalah. Nah, tapi kalau kamu di physical layer, itu kan processing tiap paket itu. Kalau misalnya kamu sekarang aja kalau kamu LTE itu 1 millisecond. Berarti AI kamu itu harus selesai within 1 millisecond. Itu kalau 4G. Kalau misalkan 5G, subcarrier-nya kamu naikin, ya kamu bagi lagi kan. 1 millisecond itu bisa jadi, kalau pakai 60 kHz bisa jadi 0,25 millisecond. Nah, kalau neural network kamu complicated, kan neural network itu at the end of the day kan kalau layer-layer itu kan sequential. Ya kamu kan masih nunggu kan. Ya itu bermasalah. Jadi desainnya juga, jadi mesti dipikirkan cara desainnya bagaimana dalam hal ini. Soalnya bermasalah. Jadi masih banyak challenge yang mesti di solve, terutama di physical layer.
Oke, mungkin sambil menunggu pertanyaan yang lain, saya juga ada pertanyaan juga. Saya tadi memperhatikan dari presentasi pertama tadi juga disebutkan bahwa machine learning lebih tepat untuk layer ke atas, dalam artian untuk layer bawah dalam hal ini physical layer challenge-nya lebih begitu ya, karena kita terbatas pada processing time-nya harus strict gitu kan. Nah, kemudian tadi beberapa risetnya Pak Wibowo mengatakan di area scheduling. Pertanyaannya adalah terkait dengan misalkan dari video yang tadi disampaikan, latensinya bisa turun kan, misal kita bisa atur apakah 10 millisecond, 6 millisecond, trade off apa yang dilakukan gitu. Artinya untuk mencapai hal itu apa yang dilakukan? Apakah ya misalkan ini apakah GPU-nya yang dinaikkan, atau kalau dari sisi metodenya apanya yang dimodified?
Oke. Untuk yang scheduling tadi ya, Pak Ajib, yang aku tadi kita punya target 6 millisecond. Target 6 millisecond itu caranya kita mencapai, kita dikasih requirement misalkan 6 millisecond gitu kan. Nah, terus dengan 6 millisecond ini kita mesti ngatur resource block-nya such that cuma deliver 6 millisecond.
Oh.
Jadi kita juga nggak tahu logiknya si AI-nya bagaimana. Pokoknya si AI-nya tuh kasih tahu, oke, untuk nyampe 6 millisecond kamu allocate resource block ini gitu untuk user ini. Kamu allocate resource block ini atau enggak kamu transmit nanti di next TTI gitu misalnya. Jadi kita juga nggak begitu jelas logiknya apa, tapi neural network-nya tuh kasih kita logik gitu. Jadi kita kayak outsource scheduling logiknya ke situ. Itu yang untuk scheduling, itu cara kerjanya begitu. Jadi idenya kan kita nggak tahu logiknya apa, tapi kita tahu requirement-nya apa. Terus kita bilang ke neural network-nya, kita punya requirement begini. Nah, terus coba tolong didesain neural network yang bisa ngeluarin logik apa kalau resource-nya butuh berapa kalau kita mau keluarin requirement ini. Itu untuk yang scheduling, kita cara kerjanya begitu. Terus kalau untuk tanya Pak Ajib tadi tentang physical layer, aku bukan bilang nggak bisa di-apply untuk physical layer, in fact actually bisa di-apply karena hasil kita untuk physical layer ternyata cukup encouraging. Jadi maksudku dalam hal ini ada hasil-hasil kita itu untuk yang pemakaian physical layer, pemakaian AI untuk misalkan di detection untuk physical layer itu bisa outperform. In fact itu bisa outperform banyak macam-macam teknik. Jadi performance-nya actually very encouraging. It's close to bisa dibilang kalau untuk certain configuration bisa close to ML, close to maximum likelihood. Tapi seperti Pak Aji bilang tadi itu ya challenge-nya itu caranya bagaimana supaya network-nya nggak kegedean. Nah itu yang mesti dipikirkan kan. Dengan itu makanya bisa kita tapi hasil result kita kelihatannya encouraging. Soalnya kenapa? Karena kalau kita ngomongin physical layer, kalau kita pakai signal processing biasa, anggap aja kita apply zero forcing misalnya gitu ya. Zero forcing itu kan inverse kan, matrix inverse. Nah kalau misalnya kita apply matrix inverse, kalau misalnya matriksnya kecil ya nggak masalah kan. Tapi kalau misalkan matriksnya besar, anggap aja misalnya matriksnya misalnya kalau OTFS jadi berapa ya? Misalkan 5.000, mungkin 10.000 sekian kali 10.000 sekian gitu. Kalau di inverse kan repot kan, bermasalah kan. Dalam hal ini AI kemungkinan bisa bantu untuk resolve masalah ini. Jadi isunya sekarang complexity. Jadi isunya satu problem. Aku rasa 5G itu problemnya jadi kompleks karena kebetulan karena jadi kompleks, mau di physical layer, mau di mac layer, kita jadi ada degree of freedom untuk cari solution. Soalnya kalau simple, standar MMSI misalnya kalau di physical layer, itu kan udah close to optimal. Kalau misalnya linear receiver kan. Terus kalau misalkan mau ditambahin lagi, tinggal taruh iterative process kan, iterative receiver kan. Di atasnya MMSI itu lebih bisa dekat ke maximum likelihood. Kalau mau ditambahin lagi bisa pakai vector perturbation kan misalnya kan. Kalau kayak lattice segala begitu kan, biar lebih dekat lagi ke ML kan. Itu kan berarti kan udah ada semua sebenarnya modelnya. Nah, tapi pertanyaannya kalau misalnya masalahnya complicated, nah itu yang, modelnya andaikan ada, modelnya tidak bisa ngeluarin solusi cepat, itu masalahnya. Kalau menurut aku physical layer.
Nah, ini yang menarik batasannya, misalkan batasannya kan masih abu-abu ya, artinya ketika kapan memakai machine learning kan tadi ada beberapa tingkatan, ada yang MMSI, ada yang ML algorithm ataupun maksudnya likelihood algorithm dan lain sebagainya dan sampai dengan vector prediction dan lain sebagainya. Nah, di atas itu ada machine learning. Nah, kira-kira batasnya ini apa gitu ya? Kapan?
Ini kita juga masih bingung. Kenapa begitu? Karena kita juga pas untuk yang simbol detector, kita kan kita recently itu juga ini kita publish paper. Oh, sorry, itu minor revision masih belum publish, masih minor revision di TICOM. Itu kita paper itu tentang iterative receiver. Tapi iterative receiver kita itu tanpa inverse. Jadi iterative receiver kita cara kerjanya dengan memakai parallel interference cancellation dan Bayesian process. Jadi pakai Bayesian, pakai inference techniques. Nah, kita pakai itu kan low complexity. Itu kita bisa mendekati ML juga untuk ini. Ya masih begitu, masih jauh, masih 2 dB, tapi udah dibanding yang lain kita udah paling dekat. Jadi tapi terus pertanyaannya kalau misalkan di skenario itu kalau kita udah dekat ke ML dengan 2 dB begitu, ya kalau misalnya pakai AI kan udah nggak ada di-improve lagi kan. Kalau di atasnya itu kan. Nah, dalam case ini ya mungkin benar udah nggak bisa di-improve. Jadi kalau gap-nya masih gede terhadap yang theoretical, nah itu mungkin AI bisa come into picture. Tapi kalau udah ada modelnya dan udah ada deket begitu, aku rasa susah gitu loh untuk improve. Soalnya kan kalau udah tinggal 2 dB terhadap lower bound untuk bit error gitu misalnya kan, AI-nya nggak bisa ini kan, nggak bisa contribute apa-apa istilahnya kan dalam hal ini kan. Tapi terus ya itu, jadi either AI-nya contribute performance atau AI-nya contribute complexity. Tapi kalau contribute complexity, kalau udah tidak ada inverse-nya, kalau pakai parallel interference cancellation, ya itu juga linear kan, ya nggak bisa. Jadi mesti lihat skenario di mana perbedaannya masih besar, atau a specific case di mana yang linear model ini tidak bisa mengapproximate atau mengeluarkan solusi yang bagus dalam hal. Jadi mesti ada skenario-nya, aku rasa harus begitu. Kalau untuk pemakaian mau di physical layer, mau di Mac layer, itu harus begitu. Jadi misalkan kayak contoh di Mac layer, kalau misalkan Pak Ajib bisa formulate resource allocation problemnya sebagai linear programming problems, ya kan? Terus tinggal tancapin simplex method, udah jalan, langsung dapat solusinya cepat kan? Nah, dapat optimal, itu kan global optimal. AI-nya juga nggak bisa contribute apa-apa dalam hal ini. Jadi harus cari skenario di mana di mana model itu fail atau modelnya tidak diketahui, baru AI-nya bisa come into picture kalau menurut aku.
Ya, masih banyak challenge sih.
Iya, masih banyak ya, kita juga baru mulai kok. Jadi kita lihat masih banyak yang ini. Nah, cuma challenge-nya kalau di physical layer biasanya karena modelnya lebih banyak diketahui. Kalau Mac layer kan lebih optimization problems, terus bentuknya kan mixed integer segala gitu. Jadi lebih tidak diketahui optimal solutionnya di mana. Tapi kalau Mac layer kan jelas, kita bisa kan ML gitu misalkan, maximum likelihood kan, nah bisa keluar kan, langsung tahu bound-nya di mana. Tapi kalau Mac biasanya lebih susah karena kita nggak tahu bound-nya di mana.
Iya. Baik. Anyway, terkait dengan tadi project yang tadi Pak Wibowo sampaikan, misalkan untuk menurunkan latency tadi ya, menjadi dari 10, 6 dan lain sebagainya. Itu end to end-nya itu berapa lama waktu untuk melakukan riset itu?
Oke. Untuk bangun interface-nya dan ngeluarin JSON-nya itu kita butuh let me see. Aku rasa 1.5 to 2 years. Itu research-nya difficult karena kita mesti ngerti hardware, terus kita juga mesti ngerti theoretical. Jadi karena itu take sometimes, dan kita juga mesti ngerti industri support kita, industri partner kita maunya apa. Ya, it take 2 years basically untuk project itu. In fact, actually that project is one of the, aku rasa aku mungkin one of the hardest project yang aku bikin. Dan satu lagi yang susah juga Huawei waktu itu. Huawei juga bikin project itu juga susah. Tapi Huawei physical layer. Tapi ini lebih susah. Kenapa? Karena kita harus prototype, kita harus demonstrate. Jadi kita harus demonstrate teknik kita ini jalan. Jadi mereka nggak mau terima kalau tekniknya cuma dites pakai simulasi. Mereka mau lihat jalan nggak ini di reality itu. Jadi I think it takes 1.5 to 2 years ya. Jadi lama, itu project yang panjang.
Baik, mungkin kita nunggu satu pertanyaan dari audiens. Sebelum kita tutup, udah hampir jam 4 ya. Halo, ada yang mau bertanya lagi? Fajar.
Izin bertanya, Prof.
Iya, silakan.
Pada penerapan machine learning ini kan ada, sebelumnya itu kan ada pemilihan fitur gitu ya. Nah, dalam pemilihan fitur ini kriteria apa yang harus dimasukkan untuk mendapatkan outputnya? Sedangkan outputnya kan kita hanya mengetahui outputnya batasannya yang ingin dicapai seperti ini. Tapi untuk pemilihan fiturnya sendiri, nah metode apa yang digunakan untuk memilih pemilihan fitur yang tepat sehingga mendapat output yang sesuai dengan yang kita inginkan. Mungkin dari saya cukup itu.
Oke, good questions. Ini yang juga hampering kita. Jadi kita sekarang di lab kita adopt two approach. Yang first itu skenario yang pertama itu yang feature-nya di mana feature-nya itu kita anggapnya sebagai dummy feature. Jadi kita masukin feature bukan untuk specific feature, tapi kita masukin feature itu sebagai dummy di mana cuma untuk increase degree of freedom-nya machine learning ya, degree of freedom. Kan kalau feature itu kan sebenarnya kan vektor kan. Jadi sebenarnya kan kalau kamu masukin ke neural network, itu kan vektor itu kan dikali-kali lagi. Itu kan sebenarnya makin banyak kan kamu bisa kayak istilahnya kayak kamu bisa create degree of freedom. Itu satu approach yang kita adopt. Itu satu approach. Yang kedua, approach yang kedua yang kita adopt, feature-nya itu kita design. Jadi kita mesti ngerti dulu feature itu bagaimana. Jadi contoh misalnya, feature-nya itu mungkin correspond to mathematical formulation. Jadi misalnya kita mau replicate specific equations. Nah, feature-nya itu mungkin komponen dari equation itu. Nah, ini aku rasa kita masih belum tahu, tapi aku rasa mungkin ini nanti ada hubungannya sama hasil terakhirnya. Kita masih investigation untuk ini. Tapi itu pandanganku begitu. Jadi kalau menurut aku, kalau aku feature itu kalau menurut aku sebenarnya harusnya kita desain, karena feature itu kan kalau misalnya kita nggak tahu kan feature itu sebenarnya kan feature problemnya kan istilahnya. Jadi kalau kita nggak tahu feature-nya, kita cuma masukin random, kita sebenarnya nggak bisa exploit feature-nya apa kan. Jadi istilahnya kita cuma berharap kita kasih random feature cukup besar di mana itu bisa keluarin establish kayak correlation atau hubungan antara feature kan. Nah, jadi ini masih nggak jelas untuk sementara ini di research kita. Kita juga masih investigate. Jadi kita investigate ke dua arah ini. Jadi kita coba yang satu feature-nya di desain, yang satu lagi feature-nya nggak didesain. Tapi recently kita merasa bahwa designing feature itu mungkin lebih bagus dibanding non-designing. Nggak design feature. Jadi feature-nya tuh jelas gitu. Feature 1 apa, feature 2 apa, feature 3 apa, feature 4 apa, itu artinya apa untuk problem kita.
Baik, terima kasih, Prof.
Baik, terima kasih. Saya kira sudah cukup ya, sudah jam 4 ini. Terima kasih atas waktunya, Pak Wibowo. Mudah-mudahan kita bisa lanjutkan dalam bentuk kolaborasi yang lain, riset dan lain sebagainya. Terima kasih, mudah-mudahan nggak bosan untuk berbagi ilmu. Baik, terima kasih. Kita ucapkan terima kasih kita mungkin foto bareng dulu kali ya. Everybody, can you turn on the camera ya? Oke. Iya, oke, good. Oke ya. Oke, ya, oke, siap ya. Sebentar ya, senyum ya. Oke, good. Terima kasih. Ya. Foto. Oke, baik. Terima kasih. Kita tutup seminar kali ini. Alhamdulillahirrahmanirrahim. Terima kasih ke Pak Wibowo dan mahasiswa semuanya. Terima kasih. Assalamualaikum warahmatullahi wabarakatuh. Dan selamat sore.
Terima kasih Pak Haji atas undangannya. Terima kasih semuanya.
Ya.
Bye.